Okay, good afternoon. Are you still there? Yes, it looks like you're still there. Excellent, thank you. All right, so today we're going to be starting our first lecture on shells, and we're going to be working with this topic for maybe 4 lectures by the end of the week, or yeah, middle of the week, and then we move on. Now, before I go any further, are there any urgent questions that you want to ask? Okay, let's move on then. So, not every problem can be solved, obviously, with solid elements. Not every problem can be solved with beam elements. Structures which are thin-walled, such as a pressure vessel, folded sheet metals, hood of a car, pop can, yeah, stuff like that, relatively thin in one direction compared to the overall dimension of the problem, has to be done with shell elements. Shell elements are essentially taking a surface. The surface can be the surface of your car roof or car hood, or the surface of the pressure vessel, propane tank, or something like that, and then you cover it with elements which look like triangles, essentially triangles, instead of pyramids that go through the thickness also, but this just covers the surface. Now, generally speaking, the condition for being able to solve it with shell element is this. Remember, at every point in your solid object, you have 6 components of stress. This is the stuff that Dr. Green did for you, okay? Now, if the stresses, there's 3 normal and 3 shears, okay? If the stresses through the thickness of your object, in other words, the normal stress through the thickness and the 2 shear stresses through the thickness, if those are small, very small compared to the in-plane one, we're going to assume they're 0, and those are appropriate for solving with shell elements. When you think about it, when you have a thin-walled structure, the stress variation through the thickness is going to be very small, okay? And therefore, thin-walled structure are perfect applications of shell elements. Now, at the end of the day, you need a surface because you're going to mesh it with shell elements. That surface, how you get it, I don't care. So I will show you a way in doing chapter 10, which is not the same way that it's done in the book. Then we're going to finish this thing, and I will come back and show it. If you wanted to do it the way the book does, what are the things that you have to worry about? The problem that we have is this folded sheet metal. Think about it as a folded sheet metal. Dimensions are given. The bottom of these edges are clamped. The bottom of these edges are clamped. And the face over here is subjected to some kind of a pressure, in this case 100 psi. Now, just like you did with the solids and beams, if there are any planes of symmetry, you have to take it into consideration. When you think about this problem, bottom clamp, same thickness of the wall, everything, and you pressurize it, if I took 1/4 of that, which is shown on the right side, 1/4 of this folded sheet metal, the behavior in the remaining 3/4 is identical. In other words, if I cut this thing along the length and along the width, you're going to get something like that. And the piece next to it, and to the left of it, and to the left of it at the bottom, they're all going to be behaving the same way. So, at the end of the day, this is the surface that you're going to model, something with these dimensions. Now, if you created this surface the way you see it on the right side, I don't care. I'm going to create this whole thing and then cut it or split it. That's entirely up to you, okay? All right. Are there any questions? Okay. So let's go to CATIA. We start with the part file, just like before. Immediately we save it. So we're going to say File, Save Management, Save As, on my desktop, a new folder, and this is lecture section 1. That's you guys. You're either in lab 51 or 52. Today is the lecture day. That's why I put down lecture section 1. And the part that I'm going to call it, the way you're supposed to do it, your student ID number, your last name, it's going to be Euler today. This is going to be lab, or let's call it like this, problem. I'll call it like this. What do I call this thing? Folded sheet direct surface, as opposed to the way it's done in the book, which first you create a solid and then out of that solid you make the surface. Okay, so we're going to say fine, that's the name of it, and now we're going to make it. Since I'm going to be dealing only with shell surfaces, I mean, you can do it in part, but at some point you have to go back to generative shape design. Now, in your case, if you have not customized your interface, you go start mechanical. What is that? Shape, and what is that? Generative shape design. Okay. All right. Good. So what I will do, I will make something that looks like that. Okay, 4.2 by 0.5. Okay, so I'm going to draw on this vertical plane. I will sketch something that looks like a C here. I'll clean it up in a minute. You have to make some cleanup here. So this one, first of all, I want to make it vertical. Okay, and then I want to make this thing symmetric. This, control that, control the middle axis. You make it symmetric. Okay, and then dimension. So this was 2. And this height is 0.5. 0.5. Okay, exit. And then you extrude it right there. Extrude. Like a pad. But there's no pad. Pad is for 3D object. And we're going to do a mirror extend. And I'm going to make it 2 in each direction. The reason I do a mirror extend because I want to be able to cut it later on. Right now, in a minute, I'm going to be cutting it like that, and I'm going to be cutting it like that. That's why I made it symmetric about the vertical axis and mirror extend. Okay. Now, in this particular problem, because of the way I did it, there is no reason to join. But if in doubt, join it. Okay. If I do it the way it's done in the book, I will have to join, okay? But here, I don't. But if it's bothering you, or if you don't know, just go ahead and join, okay? I'll leave it to you. Now, let's make this thing all out of, what is that? Yellow brass, it says? It says brass or something like that. So let's apply material to this. On this part, there is your brass. You say, okay, I don't even know why I picked brass, but anyway, there it is. Now, I will cut. So here is the split in the generative shape design. With this split, you can only cut surfaces. You cannot cut solid object. If you want to cut solid object, split solid object, you have to use the saw that is in part design. But this is a surface. We have a surface only. You select it. It says, okay, what is the element to cut? The element to cut would be this. Now, because I extruded it, it would be this. If I only joined it, whatever, it could be joined, etc. And then it says, what is the cutting element? So this middle plane, you want to take the left side or you want to take the right side? I really don't care. And you have to do another one. So split, once again, the element to cut, and the cutting element is that middle plane, and you want to take the left or the right, it really doesn't matter to us. I told you, I don't care how you get this. You could have drawn it like that. That's fine, perfectly acceptable. Let me hide these things that we don't want. Okay, good. So save everything. Now remember, save, because you already set all the initial stages of the directory and the name. All you have to do is to click on the floppy. Or you go to, if you want, File, Save Management, and you save it from here. No, I'm not going to do that. I already did it. Okay, good. We are done. We are done here. So then we're going to go to generative structure analysis, just like before. There is no solid object here. So CATIA says, okay, it's all up to you. It's all up to you. You go mesh it. Now, when I do it the book way, because first I make a box and I extract the faces of the box, there is going to be a box sitting in the background that I don't see, and immediately it gets meshed by CATIA, which I later have to go and delete and things like that. But I don't have that box. I just recreated this thing directly. Okay? Now, it's up to you. You can save your analysis right now. File, Save Management. There is your analysis, save as. In the folder that I created to you, be careful with these folders. This is not the folder that I'm doing my work right now. It's the homework that's coming up in 2 weeks or something like that, next week. So I go and I go to the folder, desktop, which I called lecture, right? There it goes. It's so easy to scroll this up. You put it in something else that opens up and you can't find it, and oh, it's a mess. 1, 2, 3, 4, 5, 6, 7, 8, 9. Euler. What do I call it? Folded sheet. Folded sheet. Folded sheet. Direct surface. Direct surface. Analysis 1, that's good. Okay, so we say okay. Now, our job is to mesh it. Mesh it with shell elements. You remember these. Solid elements, beam elements, shell element. That goes on surfaces. Look, there's no three-dimensionality into this. It goes on a surface, basically. You click on it. You select the surface. So it's going to try to put element that size for you. Notice that there is no thickness here. You can see that on this faces. Okay. Now, I'm going to make this thing a little bit smaller. So maybe 0.1. It looks just nicer. Linear, parabolic, in the absence of any information, do whatever you want. So that's fine. So it's a little bit smaller. You can look at your mesh, right-click mesh visualization, just like before. And there we are. Okay? Notice that there is no thickness to this. Just like when you did beams, there was no three-dimensionality into it. You later went and declared the cross-section of the beam as 1D property and gave the information there. It's going to be the same story here. Now, a couple of things. Notice that when I get closer here, and I put my cursor on this element, it says it's element 11, nodes 54 and 4. And if I go on the other side, it's a different element, but the nodes are still common, 54 and 4. Now, if in the way it's done in the book, I'll show you, if you don't join the nodes on this side and the nodes on that side, they're going to be different node numbers, and then you have to do some other stuff. But if you join it, that won't happen. Okay, if you join it, because it's a single surface that you mesh, basically, it won't happen. Now here, I didn't have to join, but I said, if in doubt, join it, and it's going to be the same thing. Okay. All right. Now deactivate this just like before. Deactivate. Save your analysis file by clicking on the floppy because we did all the preliminary work. Now, the bottom, this bottom is clamped. Okay? May I suggest something? While we are at it, why don't we go and define the thickness of this folded sheet metal? So I meshed it, and then I click on 2D property, 2D property, 2D property. And all it's asking you is the support. The support is this. And material was picked correctly, brass. And the thickness, it says 0.4. 0.4, that's because last time I did this thing for other people, it was 0.4, but that's a different problem. So let me see what the problem says. The thickness is 0.1 inch. So I clean this up. 0.1. And you say, OK. Okay, very good. There, right there. See that? The thickness of this and that, because it's the same surface, basically. Okay? Or if we join it, then we say, but if you don't join it, then you can have put different thicknesses. Well, let's not worry about that now. That's going to come on tomorrow on Friday. What if they have different thicknesses? Now we're going to clamp the bottom. Clamp the bottom. There's the bottom. Very good. See that? It clamped the entire edge at the bottom. Right there. Okay. Now, think about this edge and that edge. This edge and that edge. This lies in a plane which was the plane of symmetry, and it is XZ the way I have it. The way I have it is XZ. We know it's exactly the same rule as in beams. If something lies in the XZ plane, it does not move in Y. And that's a no-brainer. You think about it. Symmetry means that edge does not go to the left or right. So what we do is the user define a straight, uncheck all of these so that you start fresh. And here I will remind myself that this was XZ so that I can always check it, debug it if I make a mistake. XZ, no displacement in Y, therefore. And what are the two? There's this one and that one. And rotations opposite. So no rotation for this, no rotation for that. When something is free in translation, you fix it in rotation. When something is fixed in translation, you make it free in rotation. That takes care of this. Now this edge lies in the YZ plane of symmetry. So another one, let me uncheck all of these. I always have it of unchecking these because otherwise you can easily make a mistake. And this lies in the YZ symmetry. Symmetry. Okay. And yep, so YZ doesn't move in X. YZ doesn't move in X. And there's the edge that I'm talking about. Does not move in X. Rotation is opposite. Now, I already told you that you make these mistakes. If you incorrectly check the symmetry, you're going to lose the part marks for symmetry, all of it. Okay, there are no part marks. If you incorrectly took two, instead of taking 1/4 of this, you took half of it, you lose the part mark. You lose the marks for that particular part of the problem. Okay, and on some of these homework problems, you see a marking scheme down below. This is to give you an idea. If you had to do a problem like this, what marks you use if you, for example, made a mistake. Yeah. That's it. Load. Load was 100 psi. So we took 1/4 of that. So we put down 25 or minus 25, whichever gives you the direction of the pressure correctly. Well, obviously it's not right. We put a minus here. Let's look at it now. See that? You're pressing it down, and not a single soul is saying anything. Can you say it, please?
The person in the chat said 100 pressure.
Yes, that doesn't change. If I told you I put 100 pounds on that entire phase, I take 1/4 of it. Okay, that's good. Very good. You know why I'm asking you to say it? Because when I go to the comment, people, it has a name on it, and they may want to say something that is not right. They feel embarrassed, whatever, because I post these things on YouTube. Okay, so I have to go and delete it, edit it, blur it, blah. So this is why I say it instead of, you know. Okay, good, good, good. So let's save it and run it. Always pray. Always pray. Very good. No errors doesn't mean things are right, but no errors at least. So deflection. Okay, that sounds reasonable. That looks reasonable. Doesn't mean it's right, but it looks reasonable. I tell you why doesn't mean it's right. Because even if you didn't put these symmetries here, it would look like that. The numbers are going to be different, but it will look like that. Okay, good. Deflection. Change it to average ISO because we like color, contours, stuff like that. Okay, very good, very good. Looks like this. Now remember, these are the edges that I assume in the plane of symmetry, and so is this one. That back edge is a free surface. In other words, free edge. In other words, it's not attached to anything else. This is why the biggest displacement is actually at that corner. In other words, right next to the air, right next to nothing. The biggest displacement is not here, because here there is a little piece on this side, there's a little piece on that side, there's a little bit, and which actually provides a stiffness. It won't let this thing go as much as that guy goes. Okay, all right, good. I don't know, what are these numbers? 0.0042. Okay, it gives you some idea, but is that all you care about? Well, many people are interested in yielding and things like that. So you come here, it says 15,000 psi around that edge. That doesn't surprise you because this is a folded sheet metal with 90-degree sharp corner here. So you expect some nasty things happening there. 15,000 psi around that edge, okay? Now, do I trust these numbers? Absolutely not. Because, let me give you an example. Suppose I take you to some fellow and introduce you to that person. I say, oh, this guy is rich. How do I know? How do you know? You don't know it unless you know some other people that you can compare it against. For example, rich with respect to who? Bill Gates? Hell no. Okay. But maybe somebody, I don't know, somebody else maybe. That's the point. You ran it once. You have no reference to compare these two. So the best thing you can do, the easiest thing you can do, you know, this is the easiest one. Doesn't mean it's the final answer. Look at this. This is 15,000, right? 15,000 psi. Let me go and change this thing to a better element, parabolic. And now run it and see what the number. This is not the mesh conversion study. It's just that the fast, cheap way of having some confidence, not much. Let's look at the stress. And 18,000. You see, you went from 15,000 to 18,000. And I don't have any confidence in any one of these now. Okay? All right. This is a cheap way of maybe developing an epsilon of confidence in your result. You went from 15 to 18. Okay, that's not good. Anyway, that's not our job here. Your job, that kind of thing you do when they pay you to do it. Or you do it for your project. Something like that. Okay, so this is good. This is good. Now, I have a question for you. I would like to do this thing without using symmetry. So I'm going to kill this. Then I'm going to go to my, this is my part. I'm going to save it with a different name. File, save management. This one, save as, and I'm going to say no symmetry. How about that? This is still direct generation, direct surface, but I'm going to say no symmetry, because I don't want to lose the other one. I still want to keep it too. No symmetry. I save it under a different name. Very good. Now let's go symmetry out of the way. So there was a couple of split that I did. I'm going to delete this bottom one. Fine. I'm going to delete the next one. Fine. I'm going to save it. Okay. I'm going to go to the generative structure analysis. It's a new analysis, right? And say OK. Let's save it right away. File, save management. I've got two of them. This was the original one. This is the one that I just created. Save as, analysis. And I'm going to use the same name, except at the end, I'm going to say no symmetry. How about that? Wait a minute, that's the wrong folder. Damn. So bad, terrible. Lecture 1. There. And that name, no symmetry. So how easy it is to screw this up. No symmetry. Okay, very good. Okay. Okay. Mesh it. Why don't I use the same mesh parabolic type thing? Okay, that's fine. I can make it, I don't know, this. Notice that this number changed. That's because CATIA looks at the size of your part and based on that suggests to you something, you know, for element size. The size of the part changed and that's why it came up with its own algorithm. I can't remember what I put before. I tried to use the same one. Parabolic though, okay? All right. And I can show you the mesh, but there is no reason to do that. So let's clamp the bottom and clamp this. Okay. And then put the pressure on the top. Let's check it out. Is it in the right direction? Yep, that's in the right direction. Save it. And I'm going to run it to show you that we get an error message. You'll see. I want to show you what kind of error message you get because you anticipate that. You're going to make mistake, you forget. Look, it says thickness, you didn't tell me. See? Could not find property. Okay, let's go put a thickness there. On that same number, 0.1. Okay, this is it. Okay. Save it. Save it. And then run it. No problem. Okay, and deflection. Okay, good. Numbers. There we are. Actually, I don't think it changed that much. I don't recall what it was, but it didn't change that much. I mean, if you might say that, wait a minute, this doesn't look quite like it was before, but that's because CATIA sets a default scale for you. In other words, it will change the numbers here, change the deflection with a different scale from the previous one. So it looks more exaggerated if you want. Now remember, when I did this thing, the elements, I think I'm using the same size, parabolic, it came out to be 17,000 PSI, right? At these edges, let's check that. Yeah, look. Now, I'm sure you might say, okay, wait a minute. So why am I cutting this thing? If I can do the problem like this, I don't have to worry about those cuts. I don't have to worry about symmetries and things like that. You're right. You cut it because you want to get your marks. You cut it because if you were doing a real problem and there was 1,000,000 elements, would you put the 1,000,000 elements on this big domain, or would you put the 1,000,000 elements on the smaller domain? Obviously, the smaller domain, because the smaller the element, the more accurate the result, in principle. Okay? All right. Okay, before I do it the book way, are there any questions? No questions. Let me show you something else while we're at it. Remember those stresses in beams? we couldn't get. The only thing that you could get in beam were the axial principal stress, which is totally useless. That is not the case in shells. Shells, you can get von Mises stress, and you can get the principal stresses, in-plane principal stresses, the kind of thing that you did in more circles in your deformable bodies or stress analysis. Look, I'm going to click on it. Principal stress, right there. Principal stress. Okay, let's zoom in. Isn't that the kind of thing that you did? Because these are now two-dimensional problems. The stress through the thickness is 0. That's the assumption with shells. So this is the biggest principal stress in plane, which is 2,200. And this one is 360. There's something else that it shows you here. Look, when I plotted the von Mises stress, I got gigantic stresses at these seams, 19,000. But when you look in this area, let me just zoom in and pick with the cursor, just pick something. Look, these are 2,000. What is that? Is that 2,000? 5,000, 8,000, as opposed to 17,000. Because if you were concerned about failure here, and you were not concerned about failure there, because this is a 90-degree angle, there's no way you can have a 90-degree angle in real life, okay? There's always a bend here. It's not as bad. And if your concern must be probably there, in all likelihood, there. And the numbers are not that bad. There's about 8,000, 9,000, whatever, something like that. Not 19,000 or 17,000, okay? All right, let me kill this. So now I'm going to go and do it the book way. So I'm going to kill this completely brand new. I'm going to start with a part file. Okay. Immediately save it. File, save management, save as. The correct folder. This is not the correct folder. The correct folder on desktop. It was called lecture section 1, and I'm going to give this thing the name. So I'm going to name that I used here, okay? But I'm going to call it extracting the surface. Book way. How about the books way? No. Well, actually, I want to use the one with the symmetry. I'm going to do a symmetry, and okay. So book folded sheet metal. Not direct, extraction, which is the book way. Okay, say okay. So I'm going to create a box this size. I'm going to create a box this size, or I can create a box that size. It doesn't matter. I'm going to extract the faces. I'll leave it to you to decide which one you want. You want to do it like this, or you want to do it like that? Let me do it like this. How about that? Okay. So first of all, since you're talking about the box, you cannot be in generative shape design. You go to part design, because eventually I'm going to pad something. Part design, I can see that. On this plane, I will sketch exactly that rectangle that I had there. And I'm going to center it, because at some point I may want to cut these things. Okay, so I'm going to make it like this. Okay, let's put proper dimensions here. So this was 2. This was 2. And this guy was 0.5. 0.5. And we say okay. And we exit. And we pad it in both directions. Mirror extend. 4 inches in each direction. And we get that box. Oh, was it 4 inches or 2 inches in each direction? Sorry. This was the total thing was, this was 4. Total distance of 4, not 2. So this is going to be 2. Okay, very good. That's more like it. Very good. Okay, now you have choices here. You can put the material on it if you want. If you want to put material on it right now, we can do that. Metal, bronze. Is that what I took? Yellow, brass. I think I took black brass. I don't know. There we are. We say okay. Now, I want this face, and I want that face, and I want that face. So what I'm going to do is, as soon as you say face, that's a surface. You can't do it here. This is for part design. So you go to generative shape design, right there, okay? And look at extract. See the extract? There's this toolbar right underneath the joint thing. Maybe it's not underneath the joint, two underneath the joint, okay? One of them is extract. So you're going to extract that face. Now notice that I can't do multiple faces, but you can, if you, for example, one way of doing it, you can select them simultaneously, this, and control that. And then when you say extract, it's going to do all three of them at the same time. Okay, fine. Good. Now, I can hide this for you. I can hide the box for you. I can't delete it because these are extracted from the box. If you delete the box, these are going to go too. You can't delete it. Now, the box is sitting in the background. See that? It's right there. It's right there behind the curtain. Now, I want to cut this. Well, you do the same thing. There you are. It's that split, split. Surface to cut. Okay, now, first of all, because I did not join these, when I cut this, it's going to cut just that top piece. And I can do the side piece. So the other issue is that when you mesh something that is not joined, nodes on this side are going to be different from nodes on that side because you did not join it. Cancel that. Let's join it right there. Join. Join the side, this guy, and that guy, and that guy. All three things that you extract, join them. Because now when you cut, it's going to cut the whole thing. Later when you mesh, the mesh on the left side of the seam and the right side of the seam, they're going to be identical node numbers. Okay? So let's now try to split it. Object to cut. It's no longer just the top face. It's the join. It's the entire thing. And it says, what is the cutting element? For example, this middle one. Okay, just like what we did before. And then again, split. The entire thing is going to be picked. And the middle plane here. And it doesn't matter which side we pick. I think for you, I picked the other one just so that you don't get confused. I'll do other side. How about that? This is all dumb. But anyway, there we are. And we're going to save. I think I did the preliminary work here, right? All I have to do is to click on the floppy. It's going to do that one. Okay. Now we're going to go to generative shape structure analysis, just like before. We're retracing our steps. So CATIA immediately gives you this. That's because there is this fellow sitting in the background. It's hiding. Now, first of all, notice that when I split it with that saw, it didn't split the three-dimensional part because that saw was from generative shape design. It can only cut surfaces. But that is not the issue. What I'm saying is that it meshed the sky for me. If you don't believe it, let me bring it in the front. You see, it's there. There's my surface. There's the one that I kept for you. And there's the three-dimensional part. I don't want this, so I have to delete it. See this element? I have to delete. There, it's gone. Not only that, the 3D property that automatically did for me, this guy, that I never had to worry about it, because everything was done automatically for me, I have to delete, because otherwise it's going to come back and say, hey, I don't know what you're there, why you're there. Okay, good. Let me change the rendering here so that you can see things better. Right there. Okay. See? Solid part. So this solid part is going to be totally useless for me. But I cannot delete it because these surfaces were extracted from that. Let me hide it at least so they won't distract me. Okay? Now, mesh it the usual way. Mesh with shell element the usual way. This is what you did before. This is what you're going to do now. See that? You click on it. You select it. Okay, parabolic, fine. 0.2, fine, fine. Notice that again, because the size of this thing changed, this number changed too. This is geared internally in CATIA to the actual size of the object. If this was a mile long, this would be 200 feet, probably. There's some algorithm that they wrote that they're falling. Again, linear or parabolic. Let's use parabolic. Okay. All right. Now, you guys in section 51 or 52, on purpose, when I did the homework for, not this week, 2 weeks down the road. By the way, the homework for shells is going to be posted in YouTube today, later in the day, okay? But when I prepared the week after, on purpose, I made the element very small, and I showed you in the YouTube video for homework 4 that this will fall into a loop and it sit there for half an hour and still doesn't finish. So I had to kill the job. When you kill the job, at least I had the stuff saved beforehand, okay? So, all right, no problem. Okay, so the property, 2D property, the same thickness, nothing has changed. Brass, 0.1, these are all the same. Okay, good. And then the bottom is clamp. There we are. This is clamp. There we are. These edges are symmetry. Notice that it doesn't matter whether I take these as symmetry or these as symmetry. It's just your perspective. Another, when you cut it, did you cut it here or did you cut it on this side? This is just, I'll do the same thing as before. So this one, this edge and that edge, I'm going to uncheck all of these. And this for my own reference, so I will put down XZ symmetry, just so that I remember what this restraint is for. XZ doesn't move in Y. Rotations, opposite. Okay, another one. Let me uncheck all of these. Select that and write down YZ, YZ symmetry, YZ symmetry, symmetry. Okay, and YZ means doesn't move in X. Notice that 1, 2, 3 refers to XYZ in the global coordinate system. Unless you change this into user, you have to go pick it and make sure that later on you use the proper, association with the user. But anyway, something else. Is this good? Is this good? Does not move in X. YZ does not move in X. Should I say okay? You lose the marks for this. If this problem had 25 marks, just hypothetically, something of that, about 5 of it is going to be the symmetry constraints, and there are no part marks. So don't rush, okay? YZ does not move in X, rotations opposites. And I hope you don't look at this thing as a mean thing to do, because if we give part marks for anything that doesn't make sense, somebody might check all of these, and they say, hey, I forgot. Well, okay, but you checked all of these. You expected part marks for the ones that are correct? No, not going to happen. Okay, pressure on the top face. Make sure the direction is correct. Look, this time I have to change that thing to 100, because when these surfaces are extracted and you join them, you don't have a control over what the direction of the join is. In the previous one, I had to put a minus. This one, after the extraction process, I had to take that minus off. But the direction must be correct, and this is correct. If I put a minus sign here, it won't be correct. You're pressurizing it from the bottom. Good. Did we save this thing? I can't remember. Let me see now. File, save management. Let's see what I called it. Oh, there it is. I didn't save it. Save as. Wrong folder. I don't know why it keeps going there. There must be a way that you can fix this so that it goes to the folder that you want. I don't know how to do it. You find out, let me know. Okay, so lecture section 1, remember we did 2 analysis here from the previous one that I did, with symmetry, without symmetry, direct generation. So I want, let me take one of these, direct, okay, let me fix this thing. Yeah, this has a symmetry in it, but it's not direct. it is surface extraction, okay? So extracted surface, I don't know, something like that. Extracted surface. Extracted surface. Like the book. Okay, good. Say okay. Always save, and I did. Because if I inadvertently made this thing too small, I really didn't mean it. It's just that I put 3 more zeros there. And then when I run it, this will go into a long state of coma, and it may or may not come out of it. By that time, you may have to kill this CATIA. At least you, yeah, at least you go and, this is wrong. Let's run it. Because we're done. We're pretty much done. And I have to rush to this other defense. So if you have any questions, please send me an email or come on office hour or ask me in the lecture or the lab tomorrow. Okay, there we are. This is the deflection. This is the stress. Okay, this is the deflection. Okay, the other one was the deformation. All right, folks, I'm really sorry. I have to run. This is, we are stopping 3 minutes early. So I'm going to post this thing later on. And talk to you tomorrow. Bye. Wait a minute. How do I stop this?